Welcome. In this lecture, we're going to be talking a little bit more about those virtual functions and something called a vtable, which basically tells us why we need virtual functions. So what are we going to be covering in this lecture? We're going to be talking about how methods are called, not in a general abstract sense, in a very, very specific sense of how they're called in the machine assembly language. We are going to be looking at why we need virtual methods, and how vtables are used to implement virtual methods in C++, and how the assembly changes. We're actually going to be diving in and looking at how assembly changes when we change our code, and we're going to be using a really cool little tool to do that. Okay, so without further ado, let's go ahead and have a look at this tool. It is hosted at godbolt.org, which is the name of the developer. The tool itself is called Compiler Explorer. And I really thoroughly recommend, also linked in the resources here, is the talk by Matt Godbolt at CPP Conference 2017, so a fairly recent talk. And if you really want to dive deep on how C++ gets converted into machine code, then this is a really, really good place to go and look. But we're going to be using his Compiler Explorer website to have a look at how our code is being compiled. So let's go ahead and copy our code from the polymorphism demo and paste it into our compiler explorer.c++. Okay, and you will see that it has been compiling. It's saying it doesn't like this stud afx.h. We can just go ahead and remove that, and I'm not trying to save, I'm on the web, and it goes ahead and it actually compiles that whole program for us. And you see this scary looking thing over here on the right, which is the machine code. And actually, in fact, it's the assembly, because this will then get converted into zeros and ones. And if you really want to have a look at the zeros and ones, there's a tab across the top here where there is a zeros and ones tab. You can click on the zeros and ones tab, and this old thing down the left-hand side, it's a bit small. Let's actually expand this a little bit so it's a bit easier to see. This thing down the left-hand side, this is actually the binary of each of these instructions. So that's literally going down to what gets executed by your processor. But we're not too worried about the exact binary right now, so I'm going to zoom back out a little bit. How do I zoom back out? I go and reset it on Chrome. Okay, so this is an overview of our code, but let's first of all remove virtual and see what happens. What does our code actually look like in the most basic case, where we're just calling make noise through a pointer. So I'm going to remove my virtual in all these cases, let it recompile, which it should do in just a second. I'll just make a small code change so that it is ready to recompile. There you go. It has recompiled now. And, well, one thing that we notice is it's a lot shorter without virtual, so that's one thing. But actually, let's have a look at how we can dissect this assembly code. You'll notice that it's broken up by essentially the methods. In assembly, these are not really called methods, these are called labels, but still, same thing. It's broken up by the methods. And one thing you'll also notice is that one line of code isn't necessarily one line of assembly. If I go to this std_cout where we make an animal noise, I can actually right click on it and scroll to the assembly. Then you can see that the colors are matching there. And you can actually see that this is 1, 2, 3, 4, 5 lines of assembly just to execute this one line of code. So C++ is actually doing quite a lot for us and taking away quite a lot of the complexity. But what I'm interested in is this line here, where we do animal.makeNoise. Let's scroll to that assembly, right-click it, scroll to assembly. You'll notice this is only 2 lines of code, and one of these lines of code is very straightforward, actually. It's just a call to animal : make noise. Now, what is animal : make noise? Well, it's one of those labels, and if we translate that into binary, so if we go into our binary tab, very quickly, don't worry, I'm not going to scare you too much. Right-click on Make Noise and scroll to Assembly. Then you will see here, where is it? There is these 2 lines. Our call is just an address in memory. This 400D80 is an address in memory. It's actually translated completely away. There's no lookups or anything. And if we scroll to the address, it's a bit hard for you to see. Bit small on this monitor for some reason, but we can scroll down to 0, 400D, that's what I'm looking for, 80. You can see that it is this line here, which is the beginning of the make noise function. So what it's done there is it's literally written the code into a file, and then it's gone through and replaced all the references to make noise with the address, the first instruction that it needs to execute. And what it will do is when the CPU, gets to this call instruction, it will actually jump to the code for the make noise function. So this is completely hard coded, and it's really, really fast on modern CPUs. So that's why we don't use virtual things by default, because virtual things are a bit more complicated. Let's have a look at how they work from an abstract level. Okay, so here we have an animal pointer, and this animal pointer could be pointing to lots of different actual animals, and animals in a broad sense. Here, one could be a cat, one could be a dog, so on and so forth. But how do we know? All we've got is an animal pointer to this object. How do we know that it is a specific animal? It's a cat or a dog. How do we know which function on that animal we should be calling? This is where we have a concept called a vtable. Now, a vtable is basically a pointer that the animal itself has to this particular structure. And a structure is just a list of pointers themselves to the virtual functions, such as make noise. So this tells us where we need to go and look for the starting point of the cat's make noise function. So if I'm a piece of generic code that's just got an animal pointer and I want to call the make noise function, what I need to do is go and look at my animal, go and find its vtable. Then from the vtable, I look up the line that corresponds to a make noise function, very much like looking in the index of a book. And then I can finally jump to the address of the make noise function and execute the make noise function, safe in the knowledge that this is the cat's own make noise function, because that was the one pointed to by our cat. Now, same thing happens with the dog. The dog will have a dog vtable. So if I were to try and call make noise on this animal, then it would look in the dog vtable instead of the cat vtable, and it would go to a different address for the dog's make noise function. And finally, if I had another animal that was also a cat, it wouldn't have to point to a different vtable, it can just share the same vtable. So we only need one vtable per type, so there's a finite number at compile time, there's one per subtype. So how does this actually look when we translate it into code? Well, you could pause the video and have a go for yourself, but if you're not too confident with using the Compiler Explorer, which I fully understand, it's quite complicated, then you can go ahead and follow me. So what we're going to do is we're going to put virtual back in front of make noise, first of all. So virtual back in front of make noise. And actually, we don't need to do anything else. We don't need to override anything because we know that that was already working. We don't need that safeguard. So that's gone ahead and updated the assembly code. And I'm going to disable the binary because that's just making it look really hard to read. And I'm going to go and scroll to the line of code where we are calling animal.makeNoise. Scroll to the assembly. And you'll notice now that it's no longer calling a fixed address in memory. So that's become a little bit more complicated. But one thing that you will notice is that if we scroll towards the bottom of our file, there is a place for lots of static data that is included in the binary. And you'll notice that there is a section called the vtable for dog. There's also a vtable for animal, and somewhere in here there will be a vtable for cat as well. You can also see that there's a bunch of different constants defined in here as well, like the woof and animal noise. That's just out of interest. You can have a look at that sort of thing. But we've got vtables for cat, vtable for animal, vtable for dog, and you will notice that as part of this vtable, as part of this lookup table, here's the one for dog, there is actually that pointer again to the dog make noise label, which if we go into the binary for it and go and scroll on down to where we've got that data, I'm not sure, the data may not show up in here, or it might be near the top of the, no, it's not showing up in the binary. But if we were to look at the binary And we don't need to, but I think we can probably just hover over the label. Not quite, but we can definitely scroll to the assembly. No, we can't. But we do know that that label will get replaced at compile time by a static address. So this vtable literally just says, well, this is the entry for where the make noise function should go, and it is in this binary at this address offset. So that is why we need the virtual function, because there's so many more hops involved when we're trying to look up a virtual function, that C++'s mantra is that you don't pay for what you don't use. So when you aren't using virtual functions, there's no reason to have a vtable, and there's no reason to have to do this lookup when you could just go directly to the fixed address. Okay, so that's why we have virtual addresses, just a little bit of an in-depth foray into that, and you can have a look at Compiler Explorer in the future whenever you're wondering what is more efficient, whether this or that is going to compile down to something more efficient. Well, Compiler Explorer will show you the assembly and tell you whether it's fewer lines of assembly or not. Okay, so I look forward to seeing you in my lectures, which are going to be coming back up. For now, I'm going to hand you back over to Ben.